The internet has made engineers weirdly obsessive about bypass capacitors, size, location, do you need them, all this other stuff that it's made them tunnel vision too hard into it and it's gotten weird. So I'm going to give you one of my takes on how to do these bypass capacitors, and we're going to do it in a really unique way. So in order to inform us of what to do in the present, we're going to look into the past. So this paper here was written in 1988. So what you're going to quickly see is that the guidelines that were given to engineers like sucked, like bad, but their board still worked. So I just want to look into this so we can get an idea of what they went through. So we go to this other section, we're going to get this table of different types of capacitors, many of which we don't use this day and age, and their applications. So the ones we care about are bypassing, coupling, and maybe filtering. So a lot of them. So this is what engineers had. They had tables to work with just generic information. So another one here is capacitance, and then they had some tolerances over here. What I will note for ceramic and I guess glass, so 1,000,000 picofarads is actually 1 microfarad, so it should be extending here. So another thought you should be having is, they only went up to 1? Huh? This day and age is no big deal to get 10, 22, 47, even 100. So yeah, technology's come a long way. But once again, this is just a general table. So maximum working voltage, that's kind of important. So, and then we get, temperature stuff. And then this one I've actually seen, not just in this application note, but in general, something that looks like this. Frequency range, very important for bypassing. And so this right here is 100 megahertz. So if you go up there, they're special, what they're calling low loss. Well, for then it was low loss ceramic. So we're at, 20-ish megahertz. So this is what engineers were given. They weren't given impedance charts. They weren't given, all the normal specs we hold near and dear to our hearts. 1988, there was no Digi-Key. In fact, the internet was in its infancy. Nobody had it. So you had to deal with catalogs. Ancient catalog. Digi-Key was then. You'd have a Digi-Key catalog, not a Digi-Key website. So datasheets, well, maybe if it was in a huge catalog. So, okay. So I want to go here now. So I cannot stress to you how difficult it was to find an impedance chart of something old. I had to go with this handbook. Nobody else has this. Or I couldn't find it or something. It was such a pain in the ass to find an impedance chart. So if we're trying to get rid of noise, I got to know what frequencies there are. And I got to know what impedance is and all this other stuff. So it's this day and age, to me, this would be kind of wild to not have this chart. But nobody did back then. So just for reference, what you'll see, let me see if I still have it. So here, let me go on the left side here. And then on the right side, we're going to go here. So 68 microfarad, 20 volt, 68 microfarad, 20 volt. Also tantalum. Except this one's surface mount, obviously. This one would have been through hole. So what I want to do just to show this real quick is go straight to the right of the graph. 10 megahertz. Impedance is in the neighborhood of 2 ohms. 10 megahertz, 0.14 ohms. So that's about 15 times lower. So yeah, so your normal stuff that you're using this day and age, at the high frequency end, it's going to completely annihilate what they had back then. Capacitance wise, it should be about the same. I don't know if they, who knows what's going on about tolerance when they tested this. So another thing I do want to show you is because for ceramics in here, they didn't show an impedance chart. That's kind of wild to me. So I looked up two ones that are currently shipping. So this one is through hole. This would have been more like what you'd get back in the day. And then just surface mount. So it's almost the same thing. If you look at this resonant, I call it a resonant valley. I don't know if that's the official name. About 9 megahertz. Here we're at 20. And then high frequency, just like the tantalum, completely wastes the through hole. So, okay. But we go back in the day, all they had was through hole. Surface mount hadn't been made yet, or it was super expensive or anything like this. Through hole was the way to be back in those days. So, okay. Now we got some idea of what an application handbook or what a datasheet would have into it. Yeah, nowhere near as much detail as we have today. So it was more, they were doing it more about hopes, dreams, rainbows, unicorns. They were nothing really like this. So next thing I want to go into is the datasheet for a 68,000 processor. So back in the day, they call it 68K actually. So you might recognize these because these were used in old Apple Macintoshes. If you're a little bit younger, this is the company that makes iPhones. So this started using them in 1984. This chip, they stopped using it probably around early 90s when they changed chip families entirely to the Power PC. For vintage gamers, the Sega Genesis video entertainment system had incredible 16-bit power from its 68,000 microprocessor. So, microprocessor, because it's not for then, maybe this took a bit of power for those times, but it had no onboard storage like what we would say like flash. They'd probably have ROM and RAM. All that was off chip. So we get to here and we see some recommendations. Once again, I cannot stress to you how much of a pain in the ass was it to find anything with recommendations. Anything at all. So let's read through this. Aside from a tantalum 0.1 microfarad disc ceramics through hole. So digital circuits are notoriously noisy, and designers have learned the hard way that it is necessary to install small bypass capacitors between the plus 5-volt line and ground all over a board to keep that noise off the power lines. Okay, this day and age, I don't like it when people say, yeah, we're doing this for noise. It's too easy for people to get into like a conspiracy theory mindset of, we gotta get rid of the noise. We gotta get rid of the noise. No. What frequencies are you targeting and what are you doing to get rid of them? That's how I approach it. So the plus 5-volt is because that's what they used back in the day. There wasn't, I don't know if there wasn't 3.3 volt, but 5 was over there. And then just all over the board, that's a really general guideline. Technically, it's correct, but you'll never see it that way. So a general rule of thumb is that one such capacitor should be installed for every 2 or 3 digital ICs. Now, anybody who's not looked at this old stuff, I bet your reaction is going to be, are you shitting me? It's been freaking hammered into me. One near everything, every IC. So you're telling me I can skip Like, are they lying? Oh no, they are not lying. So if you look at this board, found it off Google Images, here, we're gonna go toward the bottom. So these yellow ones here would be your capacitors. So it's near this one, but they didn't go near here or there. They skipped every other one. Skip, 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 skip. So much skipping. Okay, these they did better. They still skipped this one, skipped. You keep going around. So this one is technically better than, oh, okay, here's the two that they, oh, well, it's next. So they technically did better than the datasheet said what to do. So, okay, so the question might be, at some point, you know, this, for its time, it was a working product. Like, it's been tested, they sold it for money, and it worked. So why they be skipping? How they be skipping is the question. So just to get it into that a little bit. So we think about, so I'm going to switch my terminology for a decoupling capacitor, decoupling all the inductive nonsense going on here. So LDIDT. So you saw in that 1980s board, I mean, they use traces, so L would be lower. So I want to talk about DIDT. Let's say this was pretty much all you had on the circuit. So you've got this thing, a trace, which has low L, and then you have high impedance here. So your DIDT is going to be really, really low. So, and we're going to assume this output has the same thing. It's going to be a trace, low L, whatever it's going to, DIDT. So what's going to go on there is, that's not going to affect this at all. Or minimal. Certainly not enough to mess with signal integrity or anything like that. So if all you had was these two items here, you could leave these capacitors off entirely, and you would be okay. There's two reasons why we put them on no matter what. One is so I don't have to worry about the rest of the circuit, what else is going on, what else is on my board, and all that. And then item number two, this thing's like a penny. So it's just not a big deal just to add one and just put it close. So I don't want you guys to be obsessing over this stuff anymore. Just look at your data sheet, what it recommends, just do that, get it kind of close, and then you will be good in most cases. So for me, when I design, I will always have one for sure, because I don't want to think about it. I got enough to think about when I'm doing design work. But when I start to think about it a little bit more, is around, if I'm going to have a DIDT of around 20 milliamps or more, that's when I'll start to think about it. So let's go back to here for just a second. For those who haven't been around the block, you might be thinking, all right, what the hell? We don't see boards like this at all this day and age. What are all these things going on here? You got to remember, these didn't have much built in compared to back in the day. So this is probably tons of buffers, logic chips like AND and OR gates, NAND, all that other stuff. RAM, ROM. So they normally did have a lot of chips. So you'll see these sockets here regularly used, probably all over these, because if you try to desolder one of these without it being in a socket, it is such a pain in the ass. So just put a socket so you can lift it out. So now I want to give you a little bit of bonus material, something that's a little bit more current, not 1980s vintage, but still gives you an idea of what's going on. So we're going to look at an FPGA from 2022. So this thing right here, maximum possible current, 50 amps. Is this for real? Oh yeah. This is probably the voltage rails are probably around 1.2 volts. So we've been doing some power here. So this will tell you what to do for capacitors. These are big boys here. So there's something like 14 caps down here, and then you got to also do this sheet. So another 18 here. So you're going to have 30 plus capacitors that are at least 10 microfarads, some much bigger. So yeah, just read your data sheets and do what they say. That's all you got to do. So, but I wanted to go even higher. So this is for motherboards for Intel processors. This particular thing is about, is there a date on here? Well, whatever. If we go to the top, it's 2008, 2009 vintage. So once you get into this, so look at this. Dynamic current step, 100 amps, and you need to be able to do 100 amps within 200 nanoseconds. So, woo, big current. So at this point, they don't even tell you what capacitors to use. They just give you an impedance guideline. So, and then if you go over here, nominal impedance, 0.8 milliohms. So there may be some kind of a, reference document for a motherboard. So, but it's probably under an NDA. So we won't get to see that. So for AMD, no dice. Forget about it. So Intel's a lot more open when it comes to this stuff. So they don't even tell you what capacitors to use. They just say, here's your impedance target, hit it. So question is, how do you do it at the level these guys are working at? What do? You've got software that can simulate this very well and then tell you what capacitors to use and placement and all that other stuff. So this is when you truly have to worry about this. You don't even have an impedance spec in this data sheet. It just tells you what to do. So for what we're doing, just do what the data sheet does. And just remember, you could, if you wanted to, in many cases, for most designs out there, you could just not have a bypass cap and you would be okay. You don't need to obsess with this. You don't need to get into the tunnel vision on it and have it take away your valuable time and brain power. So for most of what you're doing, just put the darn thing on and then move on. So there you go. If you like this video, please like it. Thank you. Bye.